Hello everyone. Today we are going to do a very important topic that is called diagonalization of a matrix. Now, diagonalization of a matrix is important because diagonal matrices are very interesting and they are very easy to deal with. So let us start diagonalization of a matrix. What is a diagonal matrix? First of all, let us learn what is a diagonal matrix. So a diagonal matrix is the one, first of all, it is going to be a square matrix. Okay. And a diagonal matrix will be the one which will have only diagonal entries. That means all the non-diagonal entries will be 0. Okay, so for example, 1, 2, 3, 0, 0, 0, 0. This is a diagonal matrix. I can write it as diagonal 1, 2, 3. That means the element, non-zero element in the first column is 1, non-zero element in the second column is 2, non-zero element in the third column is 3. That is what is meant by diagonal. So look at this D. This is diagonal D1, D2, D3. This E is diagonal E1, E2, E3. Now, why do we want to study diagonal matrices? So let us take some example. For example, I multiply 1, 2, 3, this diagonal with another diagonal 5, 0, 0, 0, 1, 0, 0, 0, 2. So when I multiply these two matrices, I'll just have to multiply the diagonal elements. That's it. And I'll get one more diagonal matrix. Okay, so that is the beauty of diagonal elements. Now, for example, if you have a diagonal matrix A, so 1, 0, 0, 0, 2, 0, 0, 0, 3. So you can see that if I raise A to the power 2, I just have to raise 1 square and then I'll be getting a diagonal whose diagonal elements will be square of the original matrix. Similarly, it goes with all the powers. So that is why diagonal matrices are very important because they're very easy to deal with. Okay. Now, what do you mean by a diagonalizable matrix? Okay. So a matrix, so we are dealing with square matrices. Okay. A square matrix A is called diagonalizable. It is a property and this property will be related to eigenvalues and eigenvectors, and that is why it is very important. So a matrix is called diagonalizable if and only if there exists an invertible matrix P, an invertible matrix P such that P inverse AP is equal to D, where D is a diagonal matrix. Okay, so if we are able to find out an invertible matrix P, which, when I do P inverse AP, I should get D. So this is also equivalent to if I pre-multiply with P on both the sides. So this is equivalent to AP is equal to PD. If I'm able to get such a situation, I will say that my matrix A is a diagonalizable matrix. Okay, so let us see how this can be achieved. For sure, what are those conditions when this can be achieved? Now, why this is important? So for example, if you have that, if A is equal to P inverse dP, because we know that we were able to write P inverse dP is equal to A. So we can write P inverse dP, P inverse is PAP inverse. Okay, so we can write D is equal to PAP inverse. So in both ways you can write. Okay, so what was my result? So I wanted to write P inverse AP is equal to D. This was my definition of diagonalization of A. That means I can write A is equal to P D P inverse. Okay, now suppose I want to calculate A square. So that will be P D P inverse, P D P inverse. Okay, so that will be P D P inverse, P D P inverse. Now P inverse P is identity. Okay, a matrix when multiplied with its inverse will give me identity matrix. So this is going to be P D square P inverse. So notice that I was doing A square here. So A square is simply, this P D square P inverse. So now A square is also a diagonalizable matrix. Okay, because D square will be a diagonal. So similarly, we can prove that A power n is P inverse D power n P. Okay, so this is the property of diagonalizable matrices. All right. Now, you should also know that eigenvalues A and P inverse AP are same. Okay, so eigenvalues of A and P inverse AP are same. What does it mean? And first of all, we should prove that. So let lambda be an eigenvalue of A. That means determinant of A minus lambda I is equal to 0. Okay, so what I can do now, I can say that determinant of P inverse A minus lambda I into determinant of P can be 0. Because note that I'm just multiplying this thing by determinants. Okay, and this determinant is already 0. And determinant of P and P inverse makes sense because P is an invertible matrix. So determinant exists for P and P inverse both. Okay, so now I can combine these determinant by the properties of determinant, that determinant AB is equal to determinant A into determinant B. So let's combine. So I have P inverse A minus lambda I, P determinant is 0. Remember that order of multiplication matrices is very important. Okay, so this implies that P inverse AP minus P inverse A lambda I into P is equal to 0. This implies the determinant of P inverse AP minus lambda I is equal to 0, because the lambda is a constant. Okay, if lambda, so if you look at P inverse lambda IP, lambda can be taken out. This is P inverse IP, which is going to be, now I is commutable identity matrix. This is lambda I P inverse P. Now P inverse P is I, so this is lambda I, so this is lambda I. Okay, so that means that lambda is an eigen value of P inverse AP. What does it mean? It means that P in, this was my D, so it means D and P inverse AP have same eigen values. Okay, now let us come to one more conclusion. Now D is a diagonal matrix. So it is a diagonal matrix D1, D2 till Dn. Eigen values of a diagonal matrix are the diagonal entries itself. So that means eigen values of D are D1, D2, Dn. This implies eigen values of P inverse AP are also D1, D2, Dn. And that means eigen values of A are D1, D2, Dn. That means we have come to a conclusion that if A is a matrix and if A is diagonalizable, then the diagonal matrix will be formed by the eigenvalues of A. So that is the first relationship between a matrix being diagonalizable and its eigenvalues, which we can always find by calculating determinant of A minus lambda I is equal to 0. Okay, so let's have a good result which gives us something to counter. Okay, so look at this theorem. An n by n matrix A is diagonalizable if and only if it has a set of n linearly independent eigenvectors x1, x till xn. Okay, in this case P inverse AP will be this matrix, okay, where lambda 1, lambda n are the associate eigenvalues. That means lambda 1 will be eigenvalue related to x1, lambda 2 will be eigen related to x2, and so on. So let us look at the proof. Okay, now we want A to be diagonalizable. Okay, so what is the definition of a diagonalizable matrix? A should be equal to P inverse dP, where P is an invertible matrix and D is a diagonal. That means your AP should be equal to dP. Okay, now AP. So now let us look at our right hand. AP should be, yeah, so this is P inverse dP. So AP should be equal to PA should be dP. Okay, or we want to use AP is equal to PD. Okay, so let's see. So how are we going to get AP is equal to PD? So we can use A is equal to P dP inverse. So AP is equal to PD because we are multiplying both sides by P. How? Post multiplying. So AP is equal to PDP inverse P. So AP is equal to PD. This is the first equation that we have formed. Okay. Now let us see. Let us call the matrix P by this form. I am simplifying the right hand side and let the diagonal entries be lambda 1, lambda 2, lambda n. We don't know anything about these lambda. We know that if A is diagonalizable, we will have a diagonal matrix and we have the formulation for P. So when we multiply, obviously I'll be multiplying the first row with first column. So that means lambda 1, P11, then okay. And then I'll be getting lambda 2, P12. So when I'll be getting this entry because P11 lambda 1 and the others will be 0. Similarly, P12 lambda 2 others will be 0. So this is my entry. So this is my AP. Okay. Now look at this formulation. This is lambda 1 x1. What is x1? X1 is this particular column. This is a way of writing lambda 1 x lambda 2 x2. So what is this x2? X2 is the second column of P. Lambda and xn. Xn is the last column of P. Okay. Now AP. So I am able to write AP is equal to lambda 1 x1, lambda 2 x2 till lambda n xn. Okay. And now what is my AP? So AP is nothing but the first column of P, the second column of P till the nth column of P. So that is nothing but AX1, AX2, AXN. So basically I'm getting AX1, AX2 till AXN, which is equal to lambda 1 x1, lambda 2 x2 till lambda n xn. So now you have got two matrices. So two matrices are equal if and only if their corresponding entries are equal. So AX1 is equal to lambda 1 x1, AX2 is equal to lambda 2 x2, AXN is equal to lambda n xn. So I am getting these equations. What is the meaning of the first equation? It means that lambda 1 is an eigenvalue of A and corresponding eigenvector is x1. Similarly, AX2 is equal to lambda x2 means lambda 2 is an eigenvalue of x2, eigenvalue of A, and corresponding eigenvector is x2. So basically, how are we getting diagonalization of a matrix? What we do, we will first find out the eigenvalues, okay? And then we will find out the vectors corresponding to them, eigenvectors. Now, P will be formed by these vectors only. So the first column of P will be the first eigenvector. The second column will be the second eigenvector. The third column will be the third eigenvector and so on. So that is how we are going to get P. Okay, so this is how this theorem is related. Now, what does the theorem says? So the theorem says that an n cross n matrix A is diagonalizable if and only if A has a set of n linearly independent eigenvectors x1, x2, xn such that this. Now, if you assume, first I assume that it is a diagonalizable matrix, and then I came to the fact that I was able to get x1, x2, xn as eigenvectors of P. Now, these eigenvectors are supposed to be linearly independent. Why? Because determinant of P is non-zero. That means rank of P is n because it is an n by n matrix. Now, what do you mean by rank of a square matrix? It is the number of linearly independent columns or rows. So how many columns are there? N columns. Rank is n. Therefore, all these n columns have to be linearly independent. Okay. So always remember how to prove that a matrix is diagonalizable or not. A matrix, so you will just have to prove that the vectors are linearly independent. And always remember one very important result. If the eigenvalues are all different, okay, अगर एक 3x3 मैट्रिक्स की 3 eigenvalues आई और तीनों के तीनों अलग हैं, then the eigenvectors associated with them are going to be linearly independent. That is also a beautiful result. So let's do a question related to this concept, okay, to understand. So let us look at this example. We have this matrix, okay, and we want to show that it is diagonalizable. Let us see, and we want to bring that form. So if you look at A, if you look at eigenvalue, so determinant of A minus lambda I will be 0. That means determinant of 1 minus lambda, 2, 3 minus lambda will be 0. That means minus lambda, 1 minus lambda, minus 6 will be 0. That means lambda, lambda minus 1, minus 6 will be 0. Lambda square minus lambda, minus 6 will be 0. Lambda square minus 3 lambda, this is splitting the middle term, will be 0. Lambda, lambda minus 3 plus 2, lambda minus 3 will be 0. Lambda plus 2, lambda minus 3 will be 0. So lambda is equal to minus 2, comma 3. So these are the eigenvalues that have been calculated. Okay. And then let us try to calculate eigenvectors. So note that both have come to be different. That means I have got my diagonal matrix. So what is my diagonal matrix? My diagonal matrix should be minus 2, 0, 0, 3. Now I want to create P. So let us try to find out an eigenvector for minus 2. So I should have AX is equal to, so 1, 2, 3, 0. Suppose it is xy is equal to minus 2xy. So I should have x plus 2y is equal to minus 2x. That means, and then I should have 3x is equal to minus 2y. So in both cases, we will get the same equation. So I should be getting y is equal to minus 3x by 2. So my eigenvector should be, my eigenvector x1 should be xy. So xy, so x minus 3x by 2. So this is x1 minus 3 by 2. So I can choose x to be 2. So it will be 2 minus 3. So this is my x1. Okay. You can choose anything. Okay. And then if you look at the second one, so I want ax. So I want ax is equal to 3x. So 3x, 3y. So I want x plus 2y is equal to 3x. So that means, and then I want, that means x is equal to y. And I also want 3x is equal to 3y. So both means x is equal to y. So I can take 1, 1. So how do you calculate your P? Remember that the first vector will be x1, the other will be x2, because x1 should be related to the first diagonal entry, x2 should be related to the second diagonal entry. So for x1, it is going to be 2 minus 3, and for x2, it is going to be 1, 1. So I have created my P, and now you just have to confirm that P inverse AP is equal to D. So if a matrix is diagonalizable, P inverse AP is equal to D, where D is the diagonal formed by the eigenvalues of the given matrix, and P is formed by the columns which are eigenvectors associated to these eigenvalues. So this is the concept of diagonalization of matrix. Again, I would like to emphasize, diagonalization of matrix is a very beautiful concept because diagonal matrices make our life easy, and therefore they are favorable for calculation purposes and applications in real life for computing theory. Thank you very much.